Okay, I want to do another tutorial today on how to use Omniprobe in the context of HIP applications. As we showed you in the last video, you can run Omniprobe to look at what's happening inside kernels running in HIP applications. And we've got a little application that runs a single instance of a kernel, and you can see if I run Omniprobe this way, I get a bunch of messages out of this kernel that tell me information. Basically, this is a timestamp. It gives me line and column information from the source file, and it tells me what work group was running, which wave within that work group, as well as where on the GPU this code was running. It tells me information about the active lane count. And from that, much information about what is happening in the kernel can be deduced. But the question is, how do we make HIP applications work this way? Well, it's really simple. We have a compile time instrumentation plugin for the LLVM compiler. We have multiple plugins actually, and they can instrument these kernels in different ways. And the way you do this is you just make sure that you compile the kernel with our particular plugin, and you'll see when I ran the shell script where it compiles the quick test application, you can see that it's using this plugin, something called lib AMD GCN submit bb start -rockem. This is the plugin that can instrument HIP applications to work properly in conjunction with Omniprobe for extracting runtime data. And you can see that it injected a basic block tracker in multiple basic blocks within the source file. If I look at that shell script, it's just an invocation of HIPCC with the -f pass plugin and then pointing at this particular plugin. We have multiple plugins. Another plugin will actually instrument every load and store or read-write operation to memory within the kernel. And this is really useful for doing a variety of memory efficiency analyses that you might want to do on your kernel to find bottlenecks. So this is all you really have to do. Now, I mean, this was simple because it was just in a shell script, but you may have a make file or a CMake application, or CMake configuration where you have to go in and integrate this particular LLVM command line switch and point at, for HIP applications, if you want to instrument basic blocks, you use that plugin. There's another plugin. Actually, let me look it up while we're doing this. I can. You can see we have several different libraries here. One is lib AMD GCN submit address messages. That's the one you want to use if you want to do memory efficiency analysis. So you pick the plugin based on the kind of analysis that you want to do, and that plugin determines what kind of messages come out of the application. The submit address messages instruments every load and store. The basic block plugin instruments every basic block. And then with that plugin, then I can pick, rather than just dump the basic messages, I can do actual basic block analysis. And I want to make sure I get JSON, and I only want a single dispatch, although I think that's all I'm going to get. And you'll see here, now I get summaries of these blocks, and I can see, individual work distribution for that dispatch. And then for every basic block, I can see, what percentage of the overall kernel overhead this particular basic block represented. You'll notice here, this is actually important. The kernel file name, it says, is unknown. Whenever the kernel file name is unknown, then the block end line and start line are indeterminate. You can't depend on them unless you have an actual file name here. In some cases, you'll have the file name. This is just an artifact of the way debug information gets written into into the binary. But you'll notice that if you have a file name, then the starting line and ending lines look more sane. But obviously, this would be a really, really big source file, and I don't think quick test is quite that large. So anytime you see a kernel file name that's unknown, then you can know that the block start and end line information is not relevant. One other thing I wanted to mention, because this might pop into somebody's mind, nothing about running and instrumenting these applications with our plugin alters the behavior of applications when they're not running with Omniprobe. I can run quick test, this little application, and it runs one kernel and I don't see any of the messages. It doesn't fail to run. The reason for that is that when we instrument these kernels, we don't actually modify the kernel that you have written or the developer's written. We actually clone that kernel and instrument the clone. And then when you run in the context of Omniprobe, Omniprobe intercepts the kernels that would normally run when you just run the application on its own and replaces them selectively with the instrumented kernels and then reads the information that is being promulgated by those instrumented kernels. So the good news is you can actually compile with these plugins and get instrumented kernels in your code, but those kernels will never run unless it runs under the context of Omniprobe. Otherwise, your application will run at full performance and be not affected by having run and instrumented with one of the Omniprobe plugins. Hopefully that makes a lot of sense. Hopefully that'll help you understand how to get started instrumenting HIP applications to run with Omniprobe. Triton's much, much easier, and I'll do another video on Triton. It's more baked in because the code gets compiled at runtime. It's a JITted environment.